All right, this was our ENGR1166 project, Turby. We're Group 13A, the men. We decided that performance was the most important aspect of the whole project. Considering the Martian colony, performance is key in making sure the colony strives. We considered cost and size as well, trying to keep the size smaller but efficient. We ended up not keeping the cost as low as we wanted, but we stayed under budget. We started off with a vertical axis wind turbine, but we quickly realized that this wasn't a realistic approach. This approach failed due to the fact that it was hard to 3D print the blades and required too much material. We realized it would be necessary to switch to a horizontal axis, which we then implemented. One idea that stuck through for us was using plywood for the base, but we ended up changing our base to a flat design rather than a box. We also ended up using glue to try to create friction so it wouldn't move, but it didn't work. To keep our turbine in place, we ended up using a brick. Another idea that stuck through was using 3D printed gears to get the motor moving.
All right, so this is our apparatus diagram. On the right, you can see our implementation of gear ratio connected to the motor and our decision to go with zinc and cork. After we switched from vertical to horizontal, most of our sketches were done on a whiteboard instead. Also on the right, you can see our decision to go with ball bearings in our vertical plywood. This was to try and reduce friction between the dowel and the plywood. And on the left, you can see a final sketch of our final product. So device iterations. On the left, you can see a very early on horizontal turbine approach. This was done with cardboard wings and a 3D printed centerpiece with a cardboard hot glued to the centerpiece, which was glued to the motor. On test day, this did rather poorly, and we decided it was not a valid long-term solution to keep using cardboard. So in the middle, you can see we opted for zinc and cork. And then on the far right, you can see we ended up going with 4 wings instead of 3 because in the Learning Community Innovation Zone, the fans are stronger. So our 3-wing did rather well. But once we reached UTEB, it stopped performing, so we had to add a 4th wing. Here's our final product. As you can see, there's the brick ballast and our gear ratio, and also we had to add a construction paper to each wing as our results were still lackluster in UTEB, but this finally helped us catch more wind. Also in this final iteration, you can see a popsicle stick dowel support. Our final readings were 91 millivolts and 0.82 microwatts.
All right, so as you can see by the data in this chart, our final product, which was the bar on the far left, that bright gold one, the power output was a lot stronger than any of our other iterations. And as you can also see, as we switched to 4 blades, it made it much more efficient from closer ranges. And as we moved back, though, for all of our different iterations, there was a significant drop-off. As you can see by the error bars, there was a approximate 5% deviation throughout all of our trials as we averaged up the different values we got. And it was kind of weird because our product was very different on test days than on actual practice days. Whereas on practice days, we were getting a lot higher outputs because we were using a stronger fan. So it's kind of weird going back and forth, adapting then as we went for the official test days. And I'm not sure if something was wrong with our microcontroller, but on the test days, a group next to us, we had the same code as them, and our blades were moving about the same speed as theirs, but they were getting in the 300 millivolt output, whereas ours was around 90 millivolts. And on the actual test day, the standard microcontroller that everybody was supposed to use for the trials was unfortunately down, so we ended up using our microcontroller, and I think the problem could have been with the motor because we had to solder another motor together because our first motor came apart, and this could have loosened the connection because today, which was after the test day, the second motor ended up falling apart too, where the wire came off again. So that could have been the reason for this discrepancy in the data, but it's to be determined. And as you can see in this video, we hit all 3 of the stretch goals. And on actual test day, we had the brick on so it did not slide backwards. And it was kind of cool. We actually got the microcontroller to have the first line have the output in millivolts. and the second line has the speed of the turbine in revolutions per second. And through Python, we were able to get both of these to happen and to get the light bulb to start to turn on whenever we begin to generate power. So that was kind of cool, and we were able to hit all through the stretch goals, which was one of our goals from the start. And total cost, our product came in at 150 of the virtual currency, and plywood was the bulk of this at almost 56%. And the next highest was sheet metal, which was 16%. And I think that was a worthwhile use of our money because that helped greatly when we switched to zinc sheets over cardboard. Whereas the plywood, I don't think that was the best use, and we didn't realize it was going to come out to that much budget. So if we were to do this again, I would definitely suggest finding a way to eliminate the plywood to make our overall product a lot cheaper. The third highest for our price was brick, and that was 6.6%. And I think that was also worthwhile because that's what enabled us to hit the third stretch goal and our final one to complete the trifecta, which was to make it not move when it was under the fan. So I think that was also worthwhile.
So as Jake said, our alternative for plywood was one of our possible future improvements, as well as spending more time to develop our horizontal wind turbine. A lot of our research time was spent on the vertical turbine, which basically went to waste. Also, for future improvements, our dowel kind of wobbled while the fan was on, so possibly opting for a thicker dowel, maybe a 1/4 inch instead of an 1/8 of an inch, would help fix this problem. The cork centerpiece also had some problems with assembly. It was difficult to assemble perfectly, so maybe going for something that was a little bit more reliable instead. And then time of delivery on ordered parts. Since we made the switch to horizontal so late in the process, it was difficult to get our ball bearings in on time. So maybe if we had more time on that, we could find a better alternative to the ball bearings.